Today we are talking about recirculation systems. Recirculation systems are characterized by coupled inlets and outlets, wherein mass, species, and particles that leave one outlet re-enter the system through one or more coupled inlets. These systems are commonly used for mixing and filtration processes. In principle, the external piping and pumping network can be modeled explicitly. In practice, however, the numerical link illustrated in this video presents a more efficient approach to model development. First, we will load the external geometry into the model. Since there is an STL file, we need to identify the length scale characterizing the system geometry. This model was built using a meter length scale, so we select meters as the relevant units upon import. We'll change to a side view really quick, and we can see that this geometry contains both an outlet drain and a dip tube that adds fluid back to the tank. We'll recenter on the Y-plane to make sure it's inside the simulation domain. We'll go to Tools, then Volume Calculator, and set the fluid volume to 30 liters and have the code compute the appropriate fill level. Now we're going to create the drain boundary condition using the edge selection option. We're going to name it Pump Out. We'll have a pump connected to this drain that draws fluid out as a user-specified flow rate of 2 liters per minute. Now we'll create the inlet boundary condition using the edge selection option. Name it Return Inlet. Change the boundary condition type to Recirculation Inlet. Link the recirculation inlet to Pump Out. Under this configuration, whatever mass, species, or particle leaves the drain is going to re-enter the system through this inlet boundary condition. The flow velocity, species, concentration, and particle injection properties of the inlet here will be governed by what is exiting the tank from the outlet. The velocity, for example, will be set on the fly to a value defined by the outlet flow rate in a manner that conserves total fluid volume. Note the options to specify a delay time and a flow ratio. The delay time represents the time interval between when species and particles leave the pump out versus when they return to the return inlet. If this is set to 1 second, for example, particles that exit through the pump out boundary condition will return into the system through the return inlet after a 1 second delay. This parameter is meant to describe the time spent by species and particles in the piping networks between the outlet and the inlet. In this case, we will set the delay time to 0, implying that species and particles immediately return into the fluid through the inlet after exiting through the outlet. The flow ratio quantifies how much of the fluid leaving the outlet drain returns through the inlet. If this ratio is set to a value less than 1, the return flow rate will be that fraction smaller than the flow rate leaving the bottom drain. Setting this parameter to a value different from 1 is only appropriate when using free surface simulations. We'll add a scalar field to the system as a cylinder positioned opposite the dip tube. We'll change the color of the child as well. This is the location where we will be adding dye to the system. The initial dye concentration in the cylinder will be set to 1 mole per liter, with an injection impulse time of 1 second. These conditions imply that, after 1 second of simulation time, dye will be instantaneously added to the fluid contained within this child cylinder with a concentration of 1 mole per liter. The total number quantity of dye added to the system will therefore be the product of this cylinder volume and this user-defined initial concentration. In time, the advection of the fluid will cause the dye to homogenize across the tank. The system initially contains no dye. The dye boundary conditions must be set up to properly handle recirculation. At the drain, we define a zero gradient boundary condition. This condition implies that the dye will exit the system with no adjustment to the arriving concentration. At the return inlet, we define a recirculation boundary condition. This implies that the concentration at the inlet will be automatically linked to the flux at the coupled outlet. Again, at both boundary conditions, we are not specifying a concentration explicitly. We are instead simply calculating what arrives at the drain and returns to the inlet. Note that the inlet has an option to specify a return value. This can be a user-defined expression. If set to the default value C, the species concentration at the return inlet will be set to a value that conserves mass flux between the inlet and outlet. In other words, the species flux leaving the outlet will be equal to the species flux back into the tank, per any user-specified delay times. If this return value were set to 0.0, none of the dye that exited through the bottom drain would return back through the inlet. This would mimic a process wherein the dye was filtered out of the recirculation line. If this value were set to 0.5 C, only half of the fluid exiting the bottom of the tank would return through the recirculation line. In this model, we have a delay time of 0 and set the return value to C, meaning that all the dye that exits through the drain instantaneously appears in the return inlet. We'll adjust the simulation resolution to 200, which increases the number of lattice points across the dip tube inlet. 5 to 10 lattice points across the inlet is generally sufficient to resolve recirculation flow. Now let's review the output control parameters. Now we'll change the volume output frequency to 0.1. We will be using the volume output to characterize the three-dimensional dye blending process across the tank. The more frequent temporal output gives us a more continuous rendering of the fluid flow and blending process. Now we'll run the code. There's no scalar field concentration in the system until 1 second. The velocity at the return inlet is defined by the flow rate at the drain. Now we'll go ahead and open MStarPost. We'll change the coloring of the 3D model to scalar concentration. Let's open the 3D view and color the system. We're going to choose the cyan to orange color scheme. And now let's march the simulation all the way to the beginning so we can see the dye being added to the system. Fluid advection is causing the dye to advance towards the drain. The dye that leaves the drain is returning through the inlet, as seen here. The effects of recirculation are to homogenize the dye across the vessel. We can see that the fluid is leaving the drain and returning through the inlet. If we go to 10 seconds, although not yet fully homogenized, the dye is spread throughout the vessel. At 20 seconds, the dye is pretty well homogenized across the fluid. Now let's create a plot of the scalar field. Following injection, the mean concentration of the dye inside the tank is constant. This is expected from the conservation of mass. We'll adjust the minimum y-axis range on the coefficient of variation plot to 1 and adjust it to a log scale. After about 25 seconds of fluid flow, the coefficient of variation converges to a constant value of about 0.03. This implies a 97% blend after about 24 seconds of mixing. This result is consistent with experimentally derived design correlations, which suggests a blend time between 20 and 30 seconds. As we play the movie back, we can see the dye entering the system, exiting the outlet, returning through the inlet, and homogenizing through the vessel after about 20 seconds. Thank you for watching this video. Please feel free to email us with any technical questions or support.